All right. Let's see. It's on? Okay. All right. Well, I guess let's go ahead and get started. So we're going to talk about network measurement tools today. My name's Jon Dugan, and I work for ESnet, which is a network that connects the Department of Energy science labs together. You may or may not have heard of us. I don't know. And so I actually asked to do a BOF on network performance tools, measurement tools, and they pushed back and said, well, how about doing a tutorial instead? And so that's how this happened. We'll see how this goes. I'd also like to introduce Jeff Boote from Internet 2, who's going to do the second half of the presentation. And he's, as you can tell, we're both from the R&E side of the house. And so as we go through this talk, hopefully, let's see. Well, basically, I'd like to encourage everyone to ask questions. If things don't seem relevant to you, or if there's just something that you don't understand, please just go ahead and stop us right over where we're at and ask the question, because we're going to cover all kinds of different ideas and tools and things today. And as a result, it's probably going to be easier to deal with it in the midst of the thing rather than trying to go, oh, where were we again when we were talking about that? So if you have a question, please just go ahead and stop and ask. So here's kind of an overview of what we're hoping that you'll get out of today. Basically, we want to provide you with an overview of what kinds of things can be measured, an introduction to some of the terms and concepts that are sort of caught up in all of this, sort of the language of this particular sub-discipline of networking, and then go into a quick overview of some of the tools that are available. There are lots and lots of network measurement tools, so we're not going to cover anywhere near all of them. And then we're going to go into a kind of a first-level introduction to a number of different tools that we're particularly familiar with. And then as throughout, there'll be lots of URLs and some different resources that you can go and look at on your own to learn a little bit more. So again, as you can see, I really like it if you ask questions, or if you know a lot about this stuff and you disagree with me, let me know. So please, let's be a little more interactive. It doesn't have to be just a lecture. I'd really prefer to have a discussion. So yeah, as I said, Jeff and I both have quite a bit of experience with these things, but I certainly don't consider myself the end-all, be-all sorts of truth on any of these things. So all right, with that said, let's just go ahead and just jump right in. Or maybe I should ask, any questions? Okay, so I'm just going to talk about the fact that there are kind of two broad camps of network measurements. There are active measurements, which are measurements where you actually inject traffic into the network. And these are generally pretty easy to interpret because you're generally sending traffic from where you are to where you want to go. And so you get pretty much exactly what you want. The problem is that they affect what you're measuring, so that you're never quite sure if what you did is what caused the change in the network or if you're measuring something, right? There's always kind of a little bit of uncertainty there. And by and large, we're going to talk mostly about active measurement tools today. There is also a whole other class of measurement tools, passive measurements, which can be a little bit harder to interpret in some ways, or sometimes they're really easy to interpret. Things like interface counters would be an example of a passive measurement, and that's pretty easy to interpret what that means. And the nice thing about passive measurements is they don't affect the network. They are just simply observing what is without actually injecting traffic into the network. All right. So here I'm just going to kind of lay out a quick taxonomy of different kinds of measurements. This is not meant to be exhaustive. It's not meant to be completely rigorous. It's just going to give you a general idea of some of the different areas we're going to talk about. So the first area is latency, which is essentially how long it takes for your traffic to get where it's going. And latency, there's basically two subcategories. There's round trip time, which is from A to Z and back from Z back to A again, and then one-way delay, which is just from A to Z. And then another thing that is common to measure is the path. And this is for example, a trace route or something like that. There are some other tools that do similar things. Then we're also going to talk a little bit about bandwidth and what do we mean by bandwidth or throughput. And there's kind of two subcategories in there that I'm going to go into a little more detail about. There's achievable bandwidth, and then there's bandwidth estimation tools. And then we'll talk a little bit about loss, and then finally do some talking about some frameworks that kind of take some of these tools and join them together or aggregate the information from the tools in a useful way. And finally, then I'll talk about some passive things, which are more the host instrumentation and traffic monitoring stuff. That's going to be pretty quick because I think that probably people are more familiar with that kind of stuff. Okay, moving right along. So think everyone would probably agree with me that the internet's a fairly complex system, and so as a result, when you're measuring it, it's difficult to know exactly what it is that you're measuring. There are many different things there, and another thing to realize is a lot of these measurements that we're making sort of at a heuristic level. We're not necessarily, we're putting traffic on the network that we expect to generate a particular behavior and using that to measure things, but filters and all kinds of other things can interfere with that sort of measurement. So we're generally using heuristics as opposed to strict rules for measuring things. A couple examples of some of the dark corners of measurement, things like path asymmetry, which is just a way of life, can cause confusion at times, especially if you're not used to looking at these sorts of things. I've suffered more pain at the MTU mismatch problems than I can possibly express. It's clearly an issue. Just every vendor has a slightly different way of implementing it, what they mean by their MTUs, and just it's a little bit more confusing, sticky issue than you'd think it would be. And then those other things like ICMP response limiting, blocking, things like tunnels. The topology you think you have, there's a whole other layer of topology hidden underneath that. Things like QoS, if there's a policer in an interface, it might radically change your bandwidth measurements, even though you have a gigabit line, it's only getting 10 megabits or something. It's all kinds of things. There's all these black holes and these dark corners, but the sort of interesting thing is people keep coming up with interesting ways to work around these limitations. And we'll see a few of these as we go on. But I just wanted to point out that it's not all gloom and doom. It's just that sometimes it's a little difficult to know exactly what it is that you're doing. Okay, so let's talk a little bit more about latency. As I said before, there's kind of basically two broad camps of different latency measurements that you make. Ping, being a round trip time measurement, is by far the most common. And that, like I said, A to Z, and then from Z back to A. How long does that take? And one way is from A to Z, and it could take the reverse path. But so the question is, okay, so one way is only half of the round trip time, right? Well, unfortunately, no, it's not that simple. Again, path asymmetry can be a problem, but things like queuing effects, the queues going one direction may be much more heavily loaded than they are going in the other direction. So it ends up that you have to measure. You're not just getting half the RTT when you're measuring the one-way delay. Sometimes you are, but that's the ideal case. Okay, another term to be aware of is jitter. Jitter is the change or the first derivative of delay, and so we'll talk about jitter a little bit. And jitter often exposes the places where there's congestion. So the most famous RTT tool of all time is ping, and a little bit later today, I'll mention a little more about throughput in a few minutes. And then Jeff's going to be talking about OWAMP later this afternoon, which is a project designed for doing one-way measurements. So, okay, so that's latency. And I guess I wanted to point out one thing is sort of interesting, right? Latency is basically determined by two factors. There's the physical length of the path. We can't beat the speed of light. I mean, even if you can do that, I'll invest in your company because you can make a lot of money. But the other thing that might cause problems for latency are, like I said earlier, queuing delays along the path. And generally the physical path is probably going to dwarf, the physical latency is probably going to dwarf the queuing delays, except for in the local area. In the wide area, it's probably going to dwarf it, but there still can be a significant component added by the queuing delays. And then just this, I guess, sort of an academic point, but loss could be thought of as an infinite latency. Okay. So as I mentioned, traceroute is the canonical tool for measuring path. And the thing is, it's important to remember that there's asymmetries involved. Things like reverse traceroute servers can help you a lot. Traceroute.org has a whole list of those, which may help you out. There's a feature that a lot of people don't know about in the IP protocol, which is the record route option. And it's implemented by at least a couple. I know Vendor J implements it in their ping, and BSD ping has it as well. And it's sort of interesting because it will actually record the route. It has some limitations in that it can only record, I think, up to 9 hops, and it's not universally implemented, but it's another interesting to look at if you've never seen it. Another tool I just wanted to point out real quick is one that sort of kind of merges together both path measurements and latency measurements, and that's MTR. And what it does is does a trace route, and then it starts to ping every hop along the way. Again, you know, like I said, there's always corner cases in these things, and if you see a sudden spike in latency to one of those hops, doesn't necessarily mean something bad happened. It might just mean that the router's gotten a bit busy and has deprioritized that sort of management traffic. Okay, so this is kind of the point that I want to get into, because I'm going to talk about Iperf for a little while, which is a tool for measuring some of these throughput issues. And so when we talk about bandwidth or throughput, it can kind of be this vague thing, right? What do we mean by throughput? Does it mean, you know, the speed of the link? What does it mean? So well, I don't think we're going to be able to replace the word throughput. I think we're going to continue to use it because that's just the way it is. But I just kind of wanted to point out some specific different areas where different aspects to what it means to get good throughput, or what factors play into getting an end-to-end throughput. So here we've got a sample path where we're going from the source to the sink. And so the capacity of any given link is its line speed, right? The capacity of any path is the capacity of the smallest link, or the narrowest link, right? So in this case, that's the 10 megabit path here, right? And that's the maximum under ideal circumstances. The best performance you could ever get out of this path is gated by this 10 megabit path or circuit. And then we can talk about the utilized bandwidth, which is how much bandwidth is used on each link. And then the available bandwidth on a given path is how much unutilized bandwidth is available at the tightest link. So in this case, this T3, this 45 megabit link here, is got less available bandwidth than the 10 megabit one. So it's the tight link. It's the limiting factor for this path. Even though it's not the smallest link, it's the tightest link. Finally, then I guess this whole point was to get to, I guess a lot of tools I'm talking about are going to be measuring what we call achievable bandwidth, which measures what you can actually force through this path. What can you actually get through this path, right? And so that takes into account the path itself. It also takes into account things like protocol overheads, or just the protocol behaviors, like TCP's way of backing off in the case of loss or congestion. And finally, it includes issues on the host. So, okay, so that's sort of a framework for what we're talking about when we're talking about bandwidth measurements. Does this diagram make sense? Are we, okay. All right, so one of the most common kinds of tools is one that measures achievable bandwidth, right? What we do, it's an active measurement. We go ahead and put traffic on the network, and we kind of we receive it at the far end and see how much traffic we got. I mean, it's a pretty straightforward idea, right? Well, it is, but there's a lot of details here. As you saw, there's a lot of interactions on the path itself. There's a lot of issues to know about tuning the individual hosts for their so that they can get the best throughput, the best achievable bandwidth. Some common examples of these kind of tools are ones that you're probably familiar with, things like NTTCP or NutTCP or Iperf. All of these tools kind of do the same thing of blasting traffic at the network and measuring what they get at the other end. And most of these tools do measure things like both UDP and TCP. Some can do other things, doing some kinds of multi-class testing. And as mentioned before, there's a tool called Throughput, which combines some of these achievable bandwidth type measurements, or it does an achievable bandwidth measurement, but it also takes note of the RTT involved in this. And it's just an interesting hybrid measurement, and it can kind of provide a little bit more insight onto what's going on. Okay, well, all right, so the next class of bandwidth measurement tools are ones that so one of the problems with the last class of tools, right, is we're sending potentially a lot of traffic into the network. We're actually inducing a load onto our links, right? So it'd be nice if we could measure how much overhead we had on a path without introducing any traffic, or at least without congesting the network itself, right? So the idea of these bandwidth estimation tools, and they've been around for a while, the idea is to send a series of packets, all very closely spaced, and at the far end, see how the spacing between them changes. And basically, this is what happens is, as the packets traverse the network, the spacing between them changes because of queuing effects at each of the intermediate hops. So this gives us an insight into the queuing behavior, and then you can apply some statistical methods to look at this and analyze what actually happened. So this works pretty well, I think, today up to, what would you say, about a gigabit today for common setups? Yeah. So this works for links up to a gigabit. The problem is you have to have really high resolution clocks to go beyond a gigabit because you have to be able to detect subtle spacing differences, and so you need better resolution on your clocks. So examples of these tools, probably the most common one today is one called PathLoad from Georgia Tech. And then there have been in the past a couple of other ones. PathCar was I think was one of the first ones by Van Jacobson. And the problem with that one is it was never actually released in a source code form. So Bruce Ma wrote a replacement for it called PCAR, which implements the same ideas but is available. I don't think there's a lot of work being done on PCAR these days, but anyway, there's the URLs if you want to go take a look at those. All right, I'm going to kind of go through this one pretty quickly because I've already taken more time than I should have. There are also some frameworks that can kind of tie all these things together. I'm going to speak about PerfSONAR here in a minute. I've got a whole slide on it. And Jeff's going to speak about BWCTL, which provides a tool framework for just doing bandwidth measurement tests of various types. And then this last one I just want to mention really quickly. Actually, one of the authors of this package said, I don't really think this fits on this slide. And I said, well, I don't know where else to put it. And I just thought something that some people might find interesting in that it provides a framework for measuring an end-to-end system, including things like the disks, not just the in-memory portions. So if you have a whole system that you need to analyze, NetLogger gives you some tools for getting logging data from all of your different points in your system so that you can kind of figure out where the issues are. I'm not going to go into a lot more detail than that, but if you have a system like that you need to measure, or if you've got a system where you're suspicious that it's the end systems that are really causing the problem and not the network, this tool might be of help for you. Okay, so I want to talk about PerfSONAR for a minute. So PerfSONAR is a collaboration between a lot of R&E networks, production R&E networks, not like networks that are doing experimental network things, but we're supporting a lot of research and education institutions. And what it is it's an attempt to build a lot of tools that can measure the networks, and then it's a set of protocols to be able to share the measurements made. And the thing is, so here's the problem that we have. We have projects like the Large Hadron Collider, which is coming online, well, very soon now. And we're going to have to be syncing about 10 gigabits of data continuously from this thing for the foreseeable future. Problem is, it's not just our network. When I say we, I mean the ESnet in this case. It's not just our network. There's several other networks in between, and so we have no real visibility into their infrastructure. So to aid this sort of project, we want to be able to exchange this performance data between, or the various different kinds of networks measurements between the different, basically, ASs in the path, right? And it's pretty interesting because one example of what PerfSONAR can do, there's one of my coworkers developed a tool where you can do a trace route through these paths that are PerfSONAR enabled, and you can actually get a bandwidth utilization graph for each hop along the way, even though only some of the hops are inside ESnet. Some of them traverse GEONT, and we even have some at CERN that all show up. And it's, I think this is a really interesting thing. It's really useful for us, but I think it could be interesting for other organizations that need to cooperate in this manner, where we're autonomous, but we're all working together to deliver this final product. All right. How are we doing for time?
It's been 20 minutes.
Okay. So then I'm just going to breeze through a whole bunch of different sort of passive measurement tools and kind of just the coarse things. So this whole talk this first talk here is really meant to just be a very high-level, quick view of all the different kinds of things that are available. So there's a lot of packet capture tools like TCP dump, Wireshark, things like NTOP and TCP trace. I'm presuming that the first ones are pretty familiar. They capture packets on the network and display them, protocol analyzer type thing. NTOP takes and summarizes what it captures off the network and produces reports. TCP trace is kind of interesting. If you have a misbehaving TCP session, you can take a TCP dump trace, run it through TCP trace, and it will give you a graph that kind of shows you some of the interactions that are happening inside the TCP state machine. And then the last one I kind of want to mention, and I'm not going to go into a lot of this, but Bro is really a security tool, but it has, what a lot of people don't understand about Bro is it has this really fabulous language underneath it for writing applications that understand network state. So Vern Paxson, who wrote it, his goal was to do things like intrusion detection and security research, and that's what it's primarily done with Bro. But it is interesting to know that there's this very, very rich language for analyzing network state and could be very useful for things well beyond just network research, or beyond security research, I mean. Okay, and then another kind of broad class of passive measurements would be flow analysis, things like net flow or S flow. And so we're going sort of, the first ones, the packet capture ones, are sort of the richest, the most granular detail. You have basically all the information at those levels. And as we get into flows, you only have a per flow information, and then finally, in something like SNMP, a very coarse granularity. All you can see is what's traversing a particular interface. You can't tell who it is at all. Okay. So the other thing I wanted to mention was the Web 100 project. I don't know if anyone here has heard of this. It's an interesting project. The main idea is that TCP is really, is very handy. It's a black box. You put data in at one end, it comes out magically at the other end, right? Except for when it doesn't. And so the problem is when it doesn't, it usually has something to do with a fairly complex interaction inside the TCP state machine. And so the idea was to put instruments inside the TCP state machine to see when different events happen. So it defines a MIB for inspecting the state of a TCP session. It has been implemented for Linux for quite a long time. At least parts of it were implemented for Windows, although I'm not sure, because I don't understand the Microsoft roadmap at all. I don't really know what product it got integrated into. But anyway, there's a lot of interesting things you can learn by looking inside the TCP state machine. And Jeff's going to talk about a project from Internet 2 called NDT, which does this, to, among other things, to make some pretty interesting observations of what was going on inside your network. All right, and then there are some other host instrumentation sort of things, which are fairly obvious. And finally, I want to leave you with a couple of URLs for some resources. If you're familiar with CADA, they have a really nice taxonomy of tools. It's slightly out of date, but there's still a lot of good stuff there. It's an interesting place to go and look. CADA is always doing interesting measurement projects. And I didn't mention some of their things because they're less end-user focused. Some of their things, like Skitter, for example, gives really wonderful information, but it's less end-user focused, not a tool you're going to use yourself. And then there's this other site here at Columbia, which is also quite good. All right, at this point, I'm going to pause for a second. Does anyone have any questions about what we've gone through so far? Anything you think I missed? All right. Let me bring up the other presentation then. Okay, so this talk is going to be much more specific than the previous one. What I'd like to talk about is a quick overview of how to use Iperf, just kind of what it can do and the common options, and a little bit of theory about how to tune TCP sessions in general. So there's probably nothing like revolutionary in here. It was hard for me to judge what level of experience people would have coming into this, so hopefully it's not too low level. If it is, I can speed up and go through, so I've got some other things at the end that are a little more in-depth. So we're going to talk about using Iperf to measure both TCP and UDP things, and then at the end I've got a collection of sort of useful tricks that I've used in the past to do things that were a little bit difficult to do with just standard tools. Okay, so I guess the first thing to say is Iperf talks about a client and a server, and this can be a little confusing because it's a little ambiguous as to what that means. So basically, the client is the entity that is sending information, sending traffic, the test traffic, and the server is the instance that is receiving the traffic and basically just discarding it. So it's a discard server. It's a client to a discard server. just want to point that out because it seems to be a common source of confusion. Okay, and so when we're talking about TCP measurements with Iperf, we're talking about achievable bandwidth, like I said before. Basically, the measurement includes the end system, and generally, though, it's just a memory-to-memory test. It doesn't involve disks, which is a whole another layer of pain. So, excuse me. There are some limits to what we can measure. Because TCP is a black box, it hides a lot of things from us. It just kind of tries to work around them, which is great because it gets its job done usually, but it can be very difficult, again, to know when it's doing that and when it's just simply another problem. Okay, so the things that can limit the performance of TCP are things like loss, congestion, buffer starvation, out-order delivery, especially with older implementations of TCP can be an issue. So there we go. All right, and using Iperf to measure a TCP session's performance is fairly straightforward. On your server end, wherever you want the traffic to go, just start up Iperf with the -s flag. It'll start listening on port 5001, and then on the client side, we just use Iperf with the -c flag and tell it the host name or the IP address of where the discard server is. By default, it'll just run a test for 10 seconds and try to see what kind of throughput it can get. So this was on my local area network at home, got 933 megabits per second, just over the local wire, no tuning required. Most things aren't quite that simple, but that's kind of the default behavior. It'll just try to open up a TCP session for 10 seconds, send as much traffic as they can in that 10 seconds, and report what it was able to measure. So, like I said, that was on the local area. That was from my my office upstairs to the server down in the basement. So it's not a very long round trip time. So in the real world, especially things that are not just inside your data center, it's important to realize that the length of the path is going to play a significant role in how TCP is going to perform. So to prevent TCP from having a lot of idle time while it waits for traffic to arrive, the sender will wait for ACKs for traffic to arrive once it's filled up its send window, right? So it's important that you set your send window the appropriate size for your path, because if you don't, it'll just send a little bit of data and then wait a long time for the ACKs to come back just because of what the round trip time is. So calculating how big this buffer should be is called the bandwidth delay product. And basically, it just tells, all it is simply the bandwidth, the maximum bandwidth you hope to achieve times the round trip time. So here's an example of the math. Basically, if you're trying to get a gigabit per second across the country, say 100 milliseconds apart, you need about 12 megabytes of in-flight data to keep TCP busy the whole time. Okay, so essentially, this is what you need to do to get full TCP performance. And must be on another slide. The -w flag to Iperf is what you use to set this. So basically, you can use ping to measure round trip time to your far end, and then do the math to determine what your bandwidth delay product is, and that will give you what the buffer size should be. Okay.
John,
yeah.
just a little bit more. The default buffer size used to be around 64K on all the systems.
Oh, right.
You see that it's really important that you set the buffer support.
Right. That's a good point.
And 64K over 100 milliseconds is
Right, right. Yeah, that's a very good. That's a very good point. So the point was that the defaults on most systems will only allow you to allocate. Well, the default without setting a window, setting the buffer size on most TCP implementations is only 64K, and many implementations won't allow you to do much more than that. They may be able to go up to like 256K or something like that. So a lot of times you have to actually change system settings in order to be able to achieve that kind of bandwidth.
Do you have a comment on whether that's a good default behavior for running Iperf on various operating systems? You see the default performance can be significantly worse on some.
So it depends. It depends a lot. I'll start and then.
Yeah, I was going to say, so most systems are changing.
The latest versions of Vista actually are much higher, for example, or they use some of the Web 100 developed auto-tuning kinds of things in order to increase that. The latest versions of Linux use auto-tuning in order to increase that. So it's not anywhere near as much of a problem as it used to be. But I mean, Linux, for example, you're not even you're most likely not even limited by Reno. But
right. Well, and the other issue, of course, is depends on what you're kind of setting yourself up for. Do you have a lot of big bulk transfers, where you're sending a lot of data, or do you have just a lot of very small sessions? So if you have millions of sessions or hundreds of thousands of sessions of this one box, the actual amount of memory that it allocates can actually be an issue, right? Because you can starve yourself. So I think the real answer is that Jeff kind of is what Jeff said, but more specifically is everything's kind of moving towards some sort of scheme which will auto-tune those buffer sizes depending on how it sees the workflow going. And there's been a lot of work done on that. All right, any other questions? Okay, so then that's the basics of how to do TCP tests. I've got a little bit more detail, which actually mentions some of the stuff we just talked about. But let's talk about UDP for a second. So one of the nice things about UDP is that it's not, if it's a black box, it's an extremely simple black box. It doesn't really tell you, it doesn't really make any promises to you. It just says, I'll do my best to get the data there, right? So the nice thing about that is it doesn't hide anything from us. So when we make these kind of tests with UDP, we actually can learn about loss because we don't have TCP hiding the loss from us. We can learn about jitter because we actually get the packets. We actually generally get interrupted every time a new packet comes in. There's some exceptions to that, but you can learn a little bit more about jitter. You can see if things arrive out of order because TCP will just put them back in order for you. These are all interesting things that we can sort of tell above and beyond just the bandwidth, but we can also see that there are other things going on in the network, and as it turns out, things like out-of-order delivery can cause performance problems for TCP. Or loss definitely causes problems for TCP. Okay, so as you can see, basically all you do is you invoke Iperf, is add the -u flag, and you do basically the same setup. I showed here also the -b, which what that will do is set your target bandwidth to 1 megabit. The deal is, with UDP, that it doesn't have any of this flow control stuff that TCP has to find a good bandwidth to you or to try to shoot for. It just does what you tell it to do. So the -b flag sets the target bandwidth. It just sets up a loop that sends at whatever data rate that you've specified. As you can see, though, or that the output's a little bit different in that it shows here. I don't know. I probably can't highlight that. Yep, I can't highlight that. So it will also show you things like the jitter here. This is expressed as 0.003 milliseconds, and then it shows the number of packets lost, the number of packets transmitted, and the loss percentage. And those things all, like I said, just basically give you those things. So here's the slide that was supposed to be earlier. Oops. Okay. So when you calculate your bandwidth delay product, you want to use the -w flag to be able to set your window size. And there are two resources here for getting information about how to tune your end systems so that they have more reasonable defaults, and also how to up the upper limits so you can get high performance transfers over long latent paths. There are also some situations where you can sort of work around TCP's fairness mechanism by actually launching parallel TCP streams. And the situations where this helps, one of the situations is where there's some loss on the path. The other one is where there's a lot of cross traffic because basically you can just, you get smaller, you get more limited, restricted streams, but you can fit more of them into the same space. At any rate, Iperf can allow you will support doing parallel transfers by just using the -p flag and specifying the number of parallel threads you want to execute. Okay. And then here's just a few simple things that are kind of handy to know. -I will give you an update on what's happening every n seconds. I didn't put it on here, but -t will set the number of seconds that you want to run the test for. And then there's things like -D, which will do the bidirectional test simultaneously. In typical invocations, it just does it in one direction and then quits. Or you can do -R, which will do one direction fully and then turn around and do the connection back. Those are all kind of handy. And let's see. All right. So at this point, how are we doing for time? Because this is sort of stuff that's...
We have about 52 minutes left.
Okay, so it's probably about time to switch.
Right.
Okay. All right, well, I'll do the one second thing on this. So I ran into a situation where all I had was a gigabit connected host, and I needed to test a 10 gigabit line. And one of my coworkers came up with this kind of harebrained scheme to do that. So turns out with these, you can use Iperf to generate a huge amount of UDP traffic. And as it turns out, receiving UDP traffic is actually kind of hard to get right. And so a lot of hosts, even like, current versions of Linux, still have trouble receiving like 9 gigabits of UDP traffic. There are things you can do. Anyway, as it turns out, there are certain router vendors whose counters I trust more than I trust counters on these hosts. So I don't really care that I can't count how much traffic I receive via Iperf. I can just use the counters on my routers. So what I did was set up firewall filters to, well, like I said, never do this, but it did actually work. So we did was we injected 1 gigabit of traffic, and we had a static route pointing to both directions on the link under test. And basically, it just was a routing loop, right? And the thing is, Iperf has a nifty little thing which says that you can set, well, this is a test situation, right? And like I said, never do this. But we had to see if we could actually stress this link. So we did is set the TTL, and the traffic went around n times and got discarded. I was a little paranoid, so I actually put a firewall filter in that also discarded it when the TTL was in a certain range, just because I wanted to make sure it went away. This actually did work quite well for us. Like I said, never do this. All right. I think that's all I've got. Anyone have any questions? All right.
Just switch power to.
Sure.
Why does it pick me rank sometimes? Okay, I'm going to talk more specifically about a couple of tools. John kind of gave more of the overview and then talked about Iperf. I'm going to go into BWCTL, OWAMP, and NDT and NPAD. And I probably should have split those up, but they're kind of similar things, so I put those together a little bit. BWCTL is something that you basically can add on top of Iperf. One of the basically, it adds resource scheduling and allocation and some policy determination to Iperf. That way you can actually have servers out there ready to do bandwidth tests or throughput tests or whatever you want to call them, and make those available to customers, to the general public, to peer networks. And that way you don't have the same sort of issues of when you're trying to debug a problem, calling up trying to find somebody who can give you an account on a system on a remote network somewhere. So, basically, the problem here is that people want to be able to verify their bandwidth when they're having some sort of performance issue. And typically, you want to do some sort of path decomposition. You want to say, okay, I'm obviously having a problem with this full path. Can I do half the path or a quarter of the path? And you're trying to break down the problem, which means you often have to set up this synchronous communication with others in order to do this kind of debugging in the typical solution with Iperf. Or any other bandwidth tool for that in that case. But so the typical roadblocks for doing this type of diagnostic exercise is that you need the same software package, either the server or the client, installed on every single host that you're going to try and test from. You're going to need some amount of permissions, usually a full shell account. You need to be able to coordinate the testing with others, and basically it ends up taking a lot of time. BWCTL was designed to alleviate that. Not actually. Let me go back a second. It was designed to help with just the ones with the asterisks there, right? You can allow tests to up to certain intensities for certain remote locations or for specific individuals even, and you can actually limit what types of things you can do. One of the nice things is that if you were to just start up an Iperf server, you pretty much have to specify that -W flag and specify that send receive buffer size when you invoke it. Since BWCTL doesn't actually open up that socket until it's actually going to run the test, it means you can actually run the test without having a remote login account at different sizes. I mean, that's one of the big issues that people end up running into when they're trying to coordinate this test with others, is they can't just throw up an Iperf server and leave it there because it doesn't have the right set of tuning options to it in order to make it a useful thing for a wide variety of tests. BWCTL's implementation is simply just a daemon and a client, and they're both built on top of the same kind of protocol library abstraction, and there's some authentication and policy hooks that can be changed by the local installation, and there's config files and all that to specify things with the normal authentication. The communication can be open or encrypted. There's one of the functionalities that BWCTL has is that it's got this concept of a three-party test. In other words, the client can actually contact two BWCTL servers and ask them to do a throughput test with each other. And this is actually one of the more useful things when you're trying to do that path decomposition, is because you could actually say, well, I know that I've already made sure that my portion of the network is clean. I've already looked at that. But the next portion, say from typically in the path decomposition test, you know someone at the remote end, you know your local end, and there's maybe 3, 4, or 5 different ASs in the middle. Now, if you can diagnose the two local ends and then diagnose the big piece in the middle separately from each other, that usually buys you a whole heck of a lot. More of the problems are on the ends than in the middle, so it's it makes it much easier if you can, say, test from your egress point from your local network to the ingress of the remote network, as opposed to full end-to-end. That way you can kind of rule out the middle, and then that's very useful in many cases, because that's where you have the longest latency issues. So if you're going to have a TCP problem, that's going to exercise it. So if that's clean, then you've pretty much, you're sure that you've got a problem in the middle, or I mean on the ends. Sorry. BWCTL the daemon basically acts as a broker for tests that come in, or for requests that come in. It's same sort of socket type of daemon as HTTP or anything else. It handles each request that comes in, decides whether it can do it given available resources. It does need most HTTP
types of daemons can actually just look at the request and decide this actually has to keep some state information, some scheduling for all new things in, so it actually has some kind of a long-lived broker process that is contacted and holds on to that kind of information. One of the other nice things about BWCTL is that both sides of the test end up with the results of the test. Typically when you're running an Iperf client, you only get the receiver side or the sender side, depending on which side you're running. And it's quite convenient to be able to get both sides from one command line invocation. And you'll see that essentially it just reps Iperf here, so you see the exact same results as from Iperf, other than the fact that you're seeing the receiver side and the sender side both, because I specified the -X flag. It essentially supports the same command line options as Iperf, with a couple of twists here and there, because of some enhancements for the authentication and some additional scheduling stuff. What I really wanted to kind of talk about a little bit here is the fact that one of the useful things about BWCTL is the fact that you can kind of set up recurring tests so that they happen over time. You know, every half an hour I want to do another one, for example. And being able to look at the historical data makes diagnosing things much easier. You know, if you knew that you did some sort of router maintenance at a given time, and suddenly your TCP tests started doing poorly after that, you know to take a look at what was changed. So this can be combined with, you know, kind of your preventive maintenance schedule in order to say, okay, what changed when the traffic started slowing down. For example, on the Internet 2 network, the backbone network, we actually have kind of a knock alarm essentially go off if any of our throughput tests from any of our POP locations go below 960 megabits per second. And then the knock is sent email. So this particular page is just showing kind of the last test that happened. And this is just a small mesh of some test servers we set up. And this is kind of what, if you clicked on any one of those, you'd get the historical record of what was, you know, of all of these tests. And, you know, you can see it's mostly a flat line going right across, but right through here, we actually had better performance for some reason, and all the rest of the time we didn't. So I didn't actually go back and try and diagnose this, but, you know, whatever we were doing during those couple of hours, we should do more often. So in order to do this resource allocation, each incoming connection is classified and determine which kind of permission set it should get. And then once it's thrown into that permission set, it finds out whether it's able to do open mode or whether it has to be encrypted, how much bandwidth to allow, how long of a test to allow, and how far into the future it can schedule tests. It basically treats the allocation of time slots for this scheduling just like any other resource in order to kind of simplify the model. And this is what the architecture looks like. I'm probably not going to go into this because it's probably not that important unless anybody wants me to, but it shows how the three-party interaction works and how that scheduling takes place. And this is what happens if you don't have a server. So if you're just doing a test from your client to a remote BWCTL server. And as I said, Iperf is the primary tester. However, the latest version of BWCTL that was just put out within the past couple months, which is still just a release candidate, and I'll be putting out another release candidate this week, I believe, if I can find a couple minutes, actually supports more throughput tools. So Throughput, which is one John also mentioned earlier today, is actually compiled into BWCTL. TCP is another one it supports. I'm actually looking at supporting some of the, or at least one of the path, the available bandwidth tools, the path load. And but essentially, the latest changes to BWCTL allow it to kind of plug in new tools as you would want. it's it's not like Java plugins. It's C code, but it's still set up as an abstraction interface. So there's just a small set of functions you would have to create in order to wrap any tool. If anyone would be interested in doing anything like that. One of the things I did want to point out is that there's problems integrating a tool by execing it, right? Which is what BWCTL does with Iperf. You don't find out. You're trying to schedule when this test is going to happen, so you give it a window of how long to allow it to run. If it hasn't finished running by the end of that window, you have to kill it so that the next test can happen. The problem is that typically when you have a problem, it exhibits itself by not finishing in terms of the Iperf test because it has completely filled its send window, and then when you go to kill it, you don't get the results from that test because it's in a low-level I/O, read or write, which means you have no idea, say, how much data was currently buffered in the send window. So the tests that fail in terms of this kind of scheduled window of stuff are usually the ones you really want the information on. So one of the things that John and I have talked about into the future is creating an API for Iperf so that you could actually get some information, and so that when you can do some actual socket interpretation at lower levels. Other things that can be done is actually integrate in some of the Web 100 tools that we've talked about earlier in order to get some of the state there. But all of these are things we've talked about for some of them, like the Web 100 one, is things we've talked about for years and never found the time to do. But the general requirements here, the latest production version of BWCTL supports Iperf 2.0 and 2.02. The latest RC version should be up to date, I think, with the latest Iperf release as of about 2 months ago. I think there may have been one since then, though.
There shouldn't be any changes for you.
Yeah, shouldn't be any changes? Okay, so we'll just say that the last one still works, too. The other things is that since you're doing a lot of these active tests and you need to be able to do kind of peer communication things, especially that three-party test I talked about, the client actually asked 2 servers to do a test. This is the exact same kind of traffic patterns that peer-to-peer networking has. So if people have a lot of filters and things to try and stop peer-to-peer networking from working, it's likely to stop BWCTL as well. And this is actually pretty out of date. Basically, almost any recent version of Unix should work just fine. And some of the policy and security considerations are that you really want to make sure that you don't end up being a denial of service source. So you need to set restrictive enough policies to disable that. And if you're running regular tests, you want to try and run your servers secure enough so that you don't end up becoming kind of a denial of service target. There's, it doesn't happen very often, I don't think, but when you're publishing your statistics in terms of what kind of performance you're getting, sometimes people like to see if they can see themselves, shall we say. Can they affect the plot somehow by sending traffic, by doing something? Sometimes that's good, actually. You want to be able to, in some of these LHC transfers, for example, that John was talking about, in supporting that, it's a very big project that we're going to have to support in getting data from CERN to many of the US universities. And you want to actually see, when the physicists spin up doing their experiment and actually consuming that data, what happens? What happens to the rest of your production traffic? In one case, just I don't know how long ago this was, about 9 months ago, I guess. The University of Nebraska physics department spun up one of their experiments to test and see how well they would be able to do once the super collider comes online at CERN. And the University of Nebraska football team was not able to transfer their scouting tape, and they were not happy. And so I mean, you end up affecting other traffic when you try and spin up new projects sometimes. And I don't know how many of you have these kinds of issues. But when suddenly one project wants to use 10 gig of a 10 gig backbone, it life interesting. So in terms of setting up a BWCTL server, the policy restrictions you want to do is you want to be restrictive for UDP tests, obviously, more liberal for TCP tests. It's going to be self-limiting, and it's good to allow others to test and figure out what kind of performance they can expect going to your system. It probably means less human time involved in order for doing diagnostics, because if they can just contact the server instead of having to contact you, life is better. And we actually implement even more liberal policies for peer networks. I mean, we've got pretty good agreements between us in terms of what they can do and what we can do, and we know who they are, so we actually tend to try and give them a little bit more so they can do more diagnostics without talking to us. The source code is available there. There's actually some RPMs available as well, and if anyone's interested, there's mailing lists as well. I'm going to go in. Is there any questions about BWCTL before I go on to the next one? Yeah. So if you go to that website, I think there is a link to several open servers. There's quite a few across the university and research and engineering networks. I don't get too much information from any commercial networks. They usually don't tell me when they have them up. I actually do end up getting email from them now and then saying, we've been using this to test things, but they pretty much use it more internally and don't make it available to others, unfortunately. So, but there is a page. If you go to this website, there will be a link on the left side, and I don't remember the actual name of the link, but and it might not be completely up to date, because in fact, ours might be one of the ones that's not, unfortunately. But there's quite a few different university networks, especially, that are there, or systems at universities. Go ahead.
Hey, James Martin from Spirit Telecom.
Hey.
Do either of you have a live distro, like a CD that you could plug into your Dell
I do,
laptop?
and I'm going to talk about it
Great.
towards the end.
Sorry.
Yep. Okay, we're going to OWAMP now, and as John said earlier, OWAMP measures one-way latencies, which is good for doing things like jitter, which I actually tend not to call jitter anymore. I usually call it delay variation, because jitter has a very specific meaning in the kind of audio-video streaming world, and it's not really the measure that I think we want to use in the networking world in general. But the OWAMP protocol was developed to isolate the directions. Typically, routing issues, congestion, many of the problems you have on networks are actually, most of the time happen in one direction, not both. So, being able to diagnose these issues separately is very helpful. The problem with trying to do one-way latencies is essentially you have to have synchronized clocks in order to measure it accurately, and you have to have coordination, right? You have to be able to say, I want to do a test at this time. And so the OWAMP was developed to do that. There is an RFC for it, which is almost 2 years old now in September. And the OWAMP implementation that I'm going to talk about was kind of the sample implementation for that. The control protocol, so OWAMP's actually two protocols, right? There's this control protocol that's a TCP protocol, and then there's the kind of more of a packet format for the test protocol. And it's UDP packets that are sent of a specific format, and they carry the timestamp information, potentially encrypted, and they're of different sizes, and they're sent at different schedules based on what was negotiated using the control protocol. And the test protocol can be open authenticated or encrypted. The difference between authenticated and encrypted is encrypted packets are completely encrypted, timestamp included. When we were working on the RFC, we decided that One of the problems with encrypting completely is that you end up getting your timestamp and then having to encrypt your timestamp, and you're spending all this time encrypting the timestamp and then sending it, and you've really perturbed your measurement a lot. Because you're not only measuring the time it took to send the packet, you're measuring the time it took to encrypt the packet and then send the packet. So we created this kind of third authenticated mode, which all of the headers in terms of things like the packet number, because there's a number, and all of the kind of information field about the packet, about what the sequence number, I guess, is actually what it's called in there, is actually encrypted first, and then the timestamp is put in the clear. That way it takes the least amount of time before it's sent. The sample implementation is actually very similar to BWCTL. I actually stole a lot of the OWAMP implementation to create BWCTL, so it looks quite a bit similar. Many tests can be set up concurrently, actually, and one of the nice features about doing an OW ping, that's the client application, is that you can actually specify completely random packet send schedules. So this is very useful if you're trying to mimic a particular traffic pattern. And it also allows you to do things like send packet trains at regular intervals, or even along basically a Poisson distribution. So you can send 10 packets on average every 1 second, or on average every 10 seconds, or something like that. That way you can see a little bit more information about what's going on in terms of packet separation, and that gives you very different characteristics with reordering and things like that on certain routing platforms. And I'm going to go ahead and skip forward to what the results look like. Essentially, if you just do a normal OW ping, what it does is it gives you a 30-second long test, or I'm sorry, a 10-second long test. Change the defaults. A 10-second long test of 10 packets per second, and it. Unfortunately, I couldn't find any interesting paths to test that actually worked for testing because of NATs and things like that. This won't work through NATs, UDP traffic, and it also so most of my test points that I have access to are on the internet to Backbone, which is a little bit over provisioned, so my data is pretty boring. But we had, in this case, there were the default test is 2 concurrent streams, 1 in each direction, for about a 10-second duration, roughly 10 packets per second. You can see that the minimum delay seen was basically 11 milliseconds, and the maximum delay seen was 11 milliseconds, and surprisingly, or not surprisingly, the median was also 11 milliseconds. And what I typically report instead of real jitter is, there I go clicking on something before I should, is the 95th percentile minus the median. So this is really just a measure of delay variation. Another common one you'll see is the interquartile spread, the 75th percentile minus the 25th percentile. The other thing that OWAMP can give you is the number of hops that the packets have traversed. It does this by setting the TTL on the send and looking at what it is at the received, and it just reports what the distribution of hops that it has seen are. And then the other thing it'll do is it'll report any reordering that it sees. And it tells you how many packets it saw that were offset by any number of degrees. So if it's offset by 3, it counts them by being at least offset by some number of packets, basically. And this is kind of what doing a historical view of that looks like. In this case, it's looking at basically the last 30 minutes worth of data, and it shows the median delay, and then also shows the lost percentage And there was no lost packets here, so I couldn't show you that it turns red and, you know, does all kinds of bells and whistles. But I was able to find one place where I could see some delay. So these plots here are actually showing the minimum, the 50th, and the 95th percentile all on one plot, and you can see that the 95th percentile actually jumps up a little bit. In fact, the median does too in a couple places here. So that's the places where there's some amount of queuing going on. And the resource allocation is very similar to the BWCTL case in that it classifies incoming connections. You can do things like have a key. I'm trying to. It's not in order to specifically identify a particular user if you're doing encryption. But most of the time what we actually use is just IP net mask types of classifications, because we pretty much try and open this up as much as possible. And this is kind of the architecture view as to how things take place. One of the big requirements that you need to do in order to really use OWAMP to its full effect is to have a very good synchronized clock. One of the things that I mentioned earlier, though, is that delay variation. You don't need to have a very well synchronized clock to do that. You just need to have fairly stable clocks for that. You'll just be willing to ignore the delay number itself, and then you can look at those differences in delay, that 95th percentile minus the median, and that'll give you a good idea of how much queuing is going on, as opposed to, because it doesn't really matter to you that your clocks are offset a whole bunch. What matters is the how much that variation is changing, if you're looking for things like jitter. And in this, again, this slide's way out of date. I really need to update this. But most recent versions of Unix should work. It's just vanilla socket code. The recommended hardware is basically, it takes almost no CPU to do this. You could do this with 10-year-old hardware pretty much. In fact, in some cases, the 10-year-old hardware works better because it doesn't have power management and it's not changing the speed of the CPU on you. But almost anything will work. The big operational concerns is that it's actually more difficult to get an accurate error estimation from NTP than it is to get a well-synchronized clock. So there's some things on the website that tell you pretty much how you need to configure NTP to make this work correctly. The bottom line is you pretty much need at least 4 NTP peers, and you should make them as diverse of paths from your local host as possible. That way you don't end up skewing your clock based on routing. NTP relies on symmetric routing, and asymmetric routing really messes it up. So the more you can do to kind of diversify your routes to remote NTP peers, the better off you are. And then there's some firewall issues. In order to send this UDP traffic through, you need to have a certain number of ports open. Part of the whole OWAMP protocol is actually kind of negotiating that port. Whoever is receiving the traffic pretty much gets to decide what port it's going to be on. So you can configure an OWAMP daemon or an OWAMP client, for that matter, to only use a specific range, and then you can have that set up in your firewall rules to say this range has to be able to receive traffic. The other part of it is that system pretty much has to be able to send traffic on any port in order for this to work, because the other side gets to decide what port it's going to be received on. So, and the policy recommendations are that the OWAMP daemon keeps track of all of the current traffic that's going on. It has global state in terms of that. So you can restrict the overall amount of traffic that any one system is going to do in terms of this. And so if you can restrict that to something you're perfectly happy going across your network, it's not an issue. And it's available on this website. And the servers should also be available on that other. And that would have been a good URL for me to put in this talk, but I didn't think of it. Is there any questions on OWAMP before I go on to the next? So I'm going to talk a little bit about two tools that are much more tuned to the end user. These are kind of advanced diagnostic tools for the end user that on the surface look something like speed test, right? So I mean, users want to be able to do this, to play in this game too. They want to, that's why speed tests and things like that are so popular. They want to be able to see, well, what kind of performance can I expect? And these tools actually are kind of an advanced version of something like that, because they don't just test to see what you could get. They try and do some amount of diagnostics to tell you why you got that. All right? So, you know, basically there's this underlying user assumption. You know, when there's a problem, it's the network's fault, right? This is kind of what we hear all the time, right? And that's because it looks like a big black hole to them. It's just this stuff in the middle that nobody gets, right? And for them, it's just the network. There's just this big, huge, amorphous blob in the middle. It left my host. It's supposed to be received by my friend's host. I'm playing a game with him, and it's not fast enough, right? In reality, it looks more like this. And trying to figure out which portion, you know, where the problem lies is, and why, is much more difficult. And quite often, you really can't see from a network operator's perspective why someone on the end is having issues, because their host is involved in the game and you don't have visibility into their host and they don't have visibility into your network. So these tools are meant to try and bridge that gap to some extent. And really, you know, so when we were Rich Carlson, who's in the same group as I am at Internet 2, you know, when he was working on this, he was really trying to attempt to answer the questions, you know, what performance should a user expect, and what is the limiting factor? Why are they getting the performance they're getting? What is the limiting factor in their transfers? Okay, and you know, what's really powerful about NDT is it allows the user to become an active participant in the debugging. It allows them to go forward and see what they're doing and see some portion of it, even if they don't understand all of it. Essentially, it tries to abstract things up to a very simple set and then give the background reasons and data behind that, and allows them to click on a button to send all those results someplace. So what we've been trying to do on the Internet 2 network and at many of the universities is to try and encourage the use of this tool as kind of a help desk front end. If someone calls up saying, you know, I'm having problems, you ask them to point their web browser at this in order to get some amount of diagnostics from the user that makes a lot more sense, that's real data, as opposed to, I'm trying to get to, some website, Wikipedia, and it's slow. That doesn't necessarily help you very much. The user interface is just a Java applet, and there's actually a command line client as well for people who want to actually test, say, server to server, which is really useful if you're trying to remote log into a POP and do a test from there. The sample results look something like this. It's still a little low level, and if someone wanted to, put lots of bells and whistles on this and make it pretty and put in a logo on it and stuff, all of our stuff's open source. So that's definitely something people could do. The things that it basically looks for right now is duplex mismatch problems, which is a big one right there. But packet arrival order, packet loss rates, and path bottleneck capacity, which does some of the same sorts of things that John was talking about earlier with the bandwidth estimation tools in order to try and figure out the bottleneck capacity. It sends a particular pattern of packets and sees what the spread of those packets are at the receiver in order to decide what kind of interfaces are in the middle. And there is a page that shows on the Internet 2 website that shows several open NDT servers out there. So, is there any questions on NDT before I go to the next one?
How does it infer the duplex mismatch?
That's an interesting one. Currently, it's doing kind of a statistical analysis. But there's actually a much better algorithm that we developed over 2 years ago that has been in copyright or in trademark issues. So we haven't been able to put that in yet, although it's my understanding that that's been resolved. I don't know, at least the other company assured me that it's been resolved and they don't care anymore, but that we haven't yet convinced our management to go ahead and do it anyway. So I'm hopeful that we'll have a much better algorithm in there soon, which actually does send some specific traffic patterns. And we've been able to determine some very specific traffic patterns that you can send that you're almost guaranteed to get a collision if you send this traffic pattern in the case of a duplex mismatch. So NPAD is a tool written by, well, I don't know if it's written by Matt Mathis, but it's under his project at, is he actually at Penn State or PSC, Pittsburgh Supercomputer. And it's very much under the same vein as NDT in that it's invoked by a web browser and you have an applet, but it's kind of looking at a slightly different problem. Actually, I should mention, the way NDT works is that it uses the Web 100 kernel variables underneath. So that's the reason it's able to do a lot of these find packet sending patterns and look at that and see what the results are, even though it's using TCP. It's able to look underneath the hood and some of the TCP stuff. NPAD's the same way, using the Web 100 things. And it's actually trying to look at the local infrastructure in general. You want to try and use NPAD to do kind of close-in tests, and it looks at the local infrastructure to try and determine whether there's anything in the local infrastructure that would limit a longer transfer. And by longer, I mean latency longer. So if you're trying to transfer something that would have a high bandwidth delay product, it looks for things that would limit that. There, Pittsburgh Supercomputer, right on the next slide. I just needed to go one more. Essentially, it's looking at that same kind of network. It's, like I said, it's looking at this long path problem. Quite often what happens is if you look here and you tried to do a transfer between like host 1 and host 2, where the path is relatively short, even if you have some sort of issue between switch 1 and R1, you might still get very good performance because your loss rate might not be so much to inhibit the transfer. Okay. Whereas if you were actually trying to send much longer, even though you're still going over that same path with the same loss rate, you end up needing to have a much lower loss rate to get good throughput in a longer distance. And there's some additional slides on this here. So essentially, in this case, in order to get the full transfer rate between host 1 and host 2, you only need to have 8 packets in flight. Okay? In order to go that longer path, you actually have to have 583 packets in flight at any one time. So the big issue here is not, let's see, go to the next one. Oh, I don't have it there. All right, I took out that other slide. So essentially what happens is because of TCP congestion control, and you cut since you cut the number of packets that can be in flight in half, the second you lose a packet and you only speed up very slowly, it actually doesn't take that long to increase up to 8 packets in flight, even if you go down to 4. It just doesn't take that long. But if you cut 583 in half and then are incrementing linearly, it takes much longer to increase that, especially since you can only do it on the order of round trip times. The main NPAD server page looks like this, and essentially, I don't know if it's large enough to see, but essentially what you can do is you can tell it the distance you are trying to go. I'm going to do a test at this local NPAD server, but I know that my actual transfer is going to be 70 milliseconds round trip time, or 100, and I want to do a test, and it adds some delay in essentially and looks at some internal statistics trying to discern if there's going to be issues with the local infrastructure. And the results look something like this. And there is a page showing several public NPAD servers out there. And then finally, we have this Network Performance Toolkit, which is a Knoppix disk that essentially is a full OS on a CD that has virtually all the tools that we've talked about today, I think. Yeah, ping and trace router there too. And it, in fact, there's also a reverse traceroute server on there. So you can actually download the ISO for this and test these tools out. It actually has a relatively sane NTP config in order to allow you to do OWAMP, and has a relatively sane set of defaults in terms of permissions for what intensities of tests to allow. And that is all I had. So if there's any questions, yeah.
Do any of those two user tools you just mentioned work over NATs, or are they the same as the previous tools?
So NDT will work over a NAT because it's just, well, I think the server to client test uses a different port number. It opens up a new connection. So you would get 75% of it would work or so. And it depends on the NAT too. I mean, some of them are smart enough that one would work, I think. The lower level tools, the BWCTL, OWAMP, and those are fairly hard to get to work right over a NAT. But the NPAD, I think, almost certainly will work completely under a NAT. I'd have to double check that, but.
So another question, I saw some V6 addresses there. Will all these tools work with IPs?
OWAMP and BWCTL were written. I had them working on V6 before I had anything working, actually. But the others, I think NDT will, but there might be. It's got its. If you're running it within an Apache web server, it should. That supports V6. It should. But I don't know if there's this built-in small web server that you can use instead, and I don't know if that one supports V6 or not. But if you're just using the CGI script from an Apache server that does that, that one should work. And I could double check that, though. I'm not 100% sure on that. Okay. Well, done 5 minutes early. Thanks.